keep on time for the scuba session, or the snorkel. I will give you a signal at 15.
My name is Joel. This is work I did with my PhD with Ross Mackenzie, University of Queensland in Brisbane. A couple of papers there. So, some of the big questions that we're looking at, particularly as physicists, are how and when does a quantum system become classical? So that diagram Ross talked about before, by this sort of dividing line between the quantum and classical world. And then particularly in this context, how and when does quantum physics matter in biology? So how can we model it when it does? Where do we see quantum effects and where do we not? And why not? And what can we see experimentally? And what can we match up to the theory? So first question is quantum mechanics in biology. Many, if not most, biochemical processes can be understood without quantum mechanics. We can do very well with ball and stick models, lock and key models for enzyme binding. And of course, quantum mechanics ultimately underlies all this, but we don't really need to understand the quantum mechanics any more than you need to understand electricity to use a telephone. We kind of shielded, the way that animated there, we sort of got, the biology is kind of shielded from the quantum physics by the chemistry. But of course, as we've already seen, there are some places where uniquely quantum effects play an important role. We have superpositions and resonances, tunneling, the juxtaposter on proton tunneling, the quantum Zeno effect, which I'll talk a little bit more about in a moment, and entanglement. Come into these various systems, photosynthesis, retinal. And so the question is, how do we determine when we will or won't see quantum mechanics on these different systems? And of course, part of the answer is that biology is hot and wet. And all that means is that biology doesn't happen in some isolated world. These chromophores, like here retinal, is embedded in a big complex protein environment. And that protein is in turn sitting inside a solvent, which you can't really see on this screen. But the point is that all of this environment is interacting with the chromophore, and it may be a major source of decoherence, as in it washes out any quantum effects. So if we want to make models of this kind of thing, we need to include the system and the bath. So how do we want to model this? Well, in physics, one of the most popular models for describing decoherence is the spin boson model. So I will go through this Hamiltonian in much more detail in a moment, but the general idea is that we have a two-level system, which could be anything, quantum dot, or in this case, biomolecules, which is coupled to a bath of harmonic oscillators. So we couple the state of the two-level system to the position of each oscillator by these coupling constants, m sub beta, which tells you how it couples to each bit of the environment. And it's been extensively studied by Tony Leggett and others. The key thing is that we don't need to know every single coupling to the environment. All that really matters is this spectral density. So this is like a weighted density of states for looking at each state of the environment and how strongly it couples to the two-level system. What Ross and I were looking at was how can we apply this Hamiltonian to biomolecules? Can we find an experimental realization of this Hamiltonian? And my computer wants to go to sleep. And we'll go through this Hamiltonian in more detail now. So the first question is, what is the two-level system? So what we can imagine is we have two biomolecules, one blue, say, and one yellow, and each has two energy levels. So if there's only one excitation available, this is effectively a two-level system. Either the blue molecule's excited, the yellow molecule's in the ground state, or, which we call sigma z is +1, or the blue molecule's in the ground state and the yellow molecule's excited, sigma z equals -1. And if these two molecules have a difference in energy of epsilon, we can write down the energy of the system like that. So that gives us a two-level system we can work with. Next thing we know is how can we couple these molecules together. Well, one thing we can use is dipole-dipole interactions. So this is a non-radiative coupling. Basically, we excite one molecule, its dipole vibrates, and that's slowly transferred over to the other molecule. What that means is we can shine in blue light, get it absorbed by one molecule, and have that excitation transferred over to the other molecule, and get out yellow light. And this is the basis of FRET, or resonance energy transfer, FRET spectroscopy. The actual efficiency of this transfer depends on the transition dipole moments of your two molecules, but also very sensitively on the distance between them. So it's used in spectroscopy as a ruler. By measuring the efficiency, you can calculate the separation of these two molecules and monitor like real-time motion of proteins, that kind of thing. But finally, we need to specify what is this environment, what is this coupling, this J of omega, to the environment. So the approach that we've been using, again, this is really bad resolution, is to look at minimal models for the environment, looking at the protein and the solvent. So the model we're using is a variation on the Onsager cavity model, some may have heard of. Basically, we treat the chromophore as a point dipole, which is sitting inside a protein which we treat as spherical. So literally the spherical cow analogy. And that protein is described as a uniform dielectric medium, some dielectric constant, possibly with frequency dependence. Surrounding that, we put the solvent, which is again treated as a uniform dielectric medium. So the nice thing about this is that all the dynamics of the protein and the solvent is captured by these dielectric constants. And while it's not going to get all the specific details, hope is this will capture the more important electrostatic interaction between the chromophore and its environment. We actually been looking at 5 different models and analysing these for the environment, including either just solvent or just protein, or solvent and protein, but also including the bound water, the water very close to the surface of the protein, which might have different relaxation properties again. I'm not going to talk too much about all of this in this talk, but we have a poster up the back, which Ross I'd be happy to talk to you about in more detail. The best model to use is going to depend on your actual system of interest, which fits better, which is most important. So to obtain the spectral density, the key physics is that the central dipole here is going to polarize your solvent. It's going to line up those solvent dipoles and indeed the protein dipoles as well. And this causes a reaction field, an electric field running positive to negative that runs through the dipole and is going to align the dipole with the electric field and stabilize the system. And this is why things dissolve in the first place. It's favourable to line up your solvent around your chromophore. And there are 2 sorts of dynamics here. The first is that the solvent dipoles are fluctuating, and should be protein as well. All of the solvent dipole is fluctuating, which is captured by these dielectric relaxations. But also the chromophore dipole changes between the ground and excited state. We saw the diagram from Smear's paper before where we had the 2 parabolas and the relaxation of the solvent there. So that's that same argument. To actually obtain the spectral density from this, what we've done is applied a fluctuation dissipation theorem to relate the fluctuations in the environment to the dissipation, which is captured by the spectral density. I'm not going to go into any details of the math because I'm sure you don't want to be bored by it, but feel free to grab the paper afterwards for more. So for these models, the spectral density we get looks something like this, depending on the model of choice. But basically, it depends on the change in dipole moment of the chromophore, the radius of the protein, and then the dielectrics of the protein and solvent. So the really nice thing is this comes out as an ohmic spectral density. So it's basically linear at low frequencies, and then it cuts off at some frequency determined by the relaxation time of your environment. And if you add sort of multiple relaxation times, what you see is sort of several peaks and dips, which again covered a little bit more detail on the poster we talked more about afterwards. the key thing is that in terms of the decoherence and the quantum behavior, the slope of this spectral density is a really important parameter. So for the chromophore in water, this slope is of order 1. The protein can shield the chromophore a little bit because the protein is much slower relaxation. But when you compare this to the coupling to the environment for things like Josephson junction qubits, where you're talking about, 0.0001, the coupling to the environment in these biological systems is very strong in terms of this two-level system coupling to its environment. So what that means is we're pretty unlikely to see quantum consciousness or quantum mechanics running out the brain or anything. So when you see what the bleep and our brains all run on, it's all bad. So yeah, that's the one important point is that there's very strong coupling in these systems. So it's going to be hard to see quantum mechanical effects. So what we're particularly interested in this context is the movement of the excitation between these two chromophores. So if I excite one chromophore, how does that excitation travel to the nearby chromophore by this resonance energy transfer dipole-dipole coupling? Well, the spin-Boson model would say you've really got three choices. Either you could have coherent oscillations where the excitation moves across, moves back, moves across, moves back, and eventually sort of stabilizes into either one or the other. In this case, it's more likely to end up on the yellow molecule with the lower energy. Or, if the coupling to the environment is a bit stronger, we might have incoherent transfer, where we basically move from one molecule to the other in sort of a smooth fashion. No coherent oscillations. If it's very strong coupling, however, we might actually see the excitation localized on one molecule, even though the molecule, nuts, might have higher energy. So this is basically like a watched pot effect, or the quantum Zeno effect, where if the environment is interacting strongly enough, you can actually trap something in a state. So which behavior you actually see is going to depend on all these different parameters. You've got the relative size, so the ratio of the coupling strength to the cutoff frequency of the environment, like sort of the relaxation time of the environment, but also the difference in energy between your two molecules, and of course the temperature. And the spin-Boson model has very rich, non-trivial dynamics. It's been very extensively studied by lots of different techniques, quantum Monte Carlo, analytical, and you can see this crossover from coherent to incoherent behavior in sort of many different ways through much different parameter space. So just one example, we have low temperatures and no bias, so we have identical molecules. For low values of alpha, that sort of measures the strength of that coupling, the slope of the spectral density. We see coherent oscillations. As you increase the coupling to the environment, we transition to incoherent. Here, if we increase it more, we end up with localized behavior. But also, if I change the temperature or reduce the coupling, I can transition up this way. So basically, we can move around these different behaviors by using all these different parameters. Adding a bias can both help or hinder these coherent oscillations. So having different colored molecules can actually increase the part of the space you can see the coherent oscillations, or decrease it. It's non-trivial, is the point. So we have these nice models which we can predict the behavior of these coherent or incoherent oscillations. The point is, can we see this experimentally? Well, the first thing is it's going to be hard. Under most sort of everyday conditions, you're going to see incoherent transfer. So particularly most of the FRET spectroscopy, where they attach different colour markers onto proteins, look at them moving around. The couplings and the temperatures that are involved here mean you're going to see incoherent transfer, which is great, because that's the classical theory that is used by experimentalists to measure distances. But there's also a non-trivial result. It's not immediately obvious that should be the case. So what can we do if we want to see this coherent behavior? Having identical molecules with epsilon, that difference in energy being 0, is a very good start. We want to have them close so the coupling is strong. But the key thing is we want to put their dipoles not parallel. I'm not actually sure what the appropriate word is there. Unparalleled, not parallel. So what we can do then is we can selectively excite one of these molecules with a polarized laser pulse. So put the pulse in perpendicular to one, but not the other. And then as this excitation moves between them, we can measure the fluorescence anisotropy as the excitation moves. So basically look at the polarization of the light that's coming out, and as that polarization changes, we'll be able to see roughly which molecule it's on. If you just see a smooth decay of the polarization, that means we're getting incoherent. If it's oscillating, we're seeing coherent oscillations. So we have a direct way of monitoring the position of this excitation in this case. And what's great for physicists is this is a highly tunable system, and relatively easy so. We can change the separation of the molecules, we can change the temperature, we can change the solvent. We can also engineer different chromophores that have slightly different properties, so different dipole moments, different energies. And these parameters can take a huge range of values over typical systems. So for physicists interested in when we have classical or quantum behaviour and the transition between them, these might be really good systems for us to play with. So bottom line is we have an experimental realization of the spin boson model in terms of these coupled biomolecules through resonant energy transfer. And we have a microscopic derivation of the spectral density through these minimal models. And these spectral densities can be compared with those you obtain from spectroscopy or molecular dynamics simulation. And the dynamics of the system can be observed directly through experiment, in theory anyway. But these models and these general ideas are applicable to other scenarios as well, which is something that hopefully will be explored more in the future. So the retinal and vision, photosynthesis, and also more complex protein models as we consider, what part of the protein or the bound water is most important, and that's the paper that we're working on at the moment. And finally, guess what I was saying before, molecular biophysics may be a really useful testing ground for these models of quantum decoherence that we have in physics. They're highly tunable and they're self-assembling. We can build quite complex systems just by using biology. So it doesn't always have to be physics helping to advance our understanding of biology. Perhaps biology can help us understand a bit more physics too. Thank you.
So, did you consider the motion of the chromophore itself in your overall relaxation process?
So you mean as in like for the transfer?
Yeah, exactly. So
no.
Or you just made it fixed?
Basically, this takes in account of being fixed. So obviously that's going to change your efficiency if they're going to move distance and everything, and all that noise. But in this perfect world, so perhaps embedded in a gel or something, particularly if we're looking at low temperatures. But yeah.
Can I look at previous slides, 2 slides before that? Yeah, before as I said, I struck it experiment. This seems to be one of the very old problems. 1970s, 60s, Cancri and Knox, they sort of studied this problem, the coupled chromophore system. And the question is here, when you excite the dimer, what is your initial state? If these two molecules are degenerate, and they are coupled to each other by this delta, delta is sizable, then naturally this dimer will form a delocalized X-inverse. It's not just a monomer it excites. So when you put some foreign agent to excite this dimer system, not the system, then probably you will excite one of the 2 excitant states, which is delocalized. And this delocalized excitant state is obtained by just diagonalizing this device. So I'm not sure whether we can really carry out that experiment specifically by controlling the polarization of the maybe you have to align these dimers specifically in three-dimensional space. And this sun-like molecule is oriented vertically along the surface. Suppose you have that linearly polarized radiation field, you selectively excite that molecule. But then again, probably you will end up with exciting localized excitation instead of monopoly excitation. Because of the coupling constant, which is not zero, and also degenerate in
Yeah, because to get the dipolar energy transfer, you have to have the dipole coupling. And whenever you have dipole coupling, then that problem
There will be.
it's a different way to explain. And the sign representation and the localized excitation representation. I think in this case, the better way to describe the follow system is localized excitation picture. So I'm not sure whether you can actually excite one molecule in reality. Is that possible?
So I think if
The polarization.
I think the key idea is the polarization is meant to be perpendicular, and so then you'd have these bonding, anti-bonding states. But what will couple, if you have the light coming in this way, that will couple to a superposition of the bonding and anti-bonding, which actually corresponds to something delocalized on that. And so you're creating that superposition, and that's then going to, basically you'll see interference effects then between the bonding and anti-bonding.
So in that sense, it's sort of quantum view.
Oh, so quantum vision. No, that's definitely the idea of the whole thing. But you'll have to have the pulse, the exciting pulse would have to be broad enough, broad enough band in frequency.
That's not actually coherent population dynamics or interaction process.
No, I'd say that is coherent. Yeah.
Do these ideas validate Penrose's ideas about brain function?
There's like in the brain. So do you mean the
Quantum. It's a quantum. Have quantum. Basically, quantum behavior that dominates the entire cognitive behavior.
Well, I would say very much no.
It doesn't invalidate. Too many double negatives, sorry.
There's no quantum in the brain. The time scales that you're looking at, I mean, the coupling here is very strong. The time scales you're looking at, the decoherence of the wave function or any superpositions is going to happen on a time scale far shorter than any of the neural processes we have here, any of the transmission of electrical impulses. So it seems pretty unlikely that these, many orders of magnitude smaller quantum processes could really be affecting. Right? They do have these sort of various ideas where you have more complex qubits that are somehow stored in geometric shapes, but basically there's no real evidence to that effect. So.
Well, if that's the case, the title of his book, The Emperor's New Clothes, is more apposite than you thought.
There was a paper by the cosmologist Max Tegmark, which essentially made this point repeatedly, that there was no way you could easily have coherence. So
what is the time scale? I think I've discussed this across the board. What is the time scale you expect for these to occur? Depends on the molecule.
For the transfer here, basically it depends on the coupling between them. But I think on the order of like picoseconds.
Sometimes it will be femtosecond. It really varies. In terms of frequency, thinking in terms of centimetres to the -1 of what delta is, and then you can probably convert that in your head, and I can't. But you go anything from 1 centimetre to the -1 to 100 centimetres to the -1. So in some of the photosynthetic, like spectral pair and stuff, we're talking a few hundred centimetres to the -1. Is that right? I don't know what that converts to in That's less than 10 per second. So,
I hope it's not less than 10%.
I think it's sort
I
of
think it is, yeah. So,
110 per second.
Other questions? Okay, well, thanks again. For very quick talk.
So, by noon,